Hello, everyone. We are very happy to be here. I hope everybody enjoyed the week off. If you can hear me, please put a thumb up or something, or say I hear you in the chat. As we know, there is a little bit of a delay. Can you hear me? Just to be sure. Still a delay. There are high hands. I hear you.
Okay. Yeah. Mm-hmm.
Thank you. So we are very delighted to be here after a 1 week break. We missed everybody. We missed the salon. I personally missed especially John and Jovo. And so I'm very happy that we can all gather and enjoy this week's wonderful philosophy session. So as a reminder, the salon is a weekly gathering where we sort of meet friends and colleagues to discuss the contentions and bridges between biological and artificial learning and topics that are related to them. We are respectful of each other. We have a flat hierarchy and have socially progressive norms. So please be respectful of everyone else. Feel free to disagree with others, but please respect everyone in spite of intellectual disagreement. We find ourselves to be very privileged to have this community on a weekly basis, and we need to thank Worldwide Neuro for making it possible. And we have help behind the scenes from Kanaka, Brad, Claire, and Eva, and we want to thank them very much. And they will be during the chat. If you have any clarification questions, you can put it there. They will help you out. They will amplify your questions if we are discussing on screen and we miss something in the chat. And also, we think that it's an entirely different skill to be smart on paper and a totally different skill to discuss and converse for a long time and answer questions with a lot of people. And we hope that this salon creates an environment where if you're especially if you're either underrepresented person in science or if you're junior in your career, that you would engage in the skill of multidisciplinary conversation. So please feel free to ask a question, even if you feel like you're not an expert or if you feel like you're a junior scientist, we still want to hear your questions. As a reminder, below there is an ask a question button. Enter your question there and please vote on each other's questions. And yeah, one more thing before John introduces our wonderful guest today is I don't know how many of you have heard about the firing of Timnit Gebru from Google because she had written a paper that uncovered bias in language models, and it had been approved. Months afterwards, they found some technical reasons to sort of ask her to roll it back. And it seems like the reasons are not entirely clear, but it seems like they wanted her to cite some more papers. But it seems kind of strange that they did that. And it also seems strange that she got fired for speaking up against that in a group that was called Women and Allies. You can read both of the emails in the link that I have entered at the top of the chat. And I'm going to enter the link again here. We, of course, stand in solidarity with Timnit, who is a leader and a very important thinker in the field of AI, in the field of revealing bias. She's the founder of FACT-like conferences on fairness and in machine learning. She's someone that a lot of us look up to. She's been a role model and mentor at Queer in AI, at Black in AI, and the fact that this is what happened is something that a lot of us are standing in solidarity with her. So with that, I'm going to turn to Jovo, and he wanted to say something about this, I think, and then John will introduce our wonderful guest. You're muted.
Okay, thanks, Haida. Yeah, so, I obviously heard about this news earlier. My whole Twitter feed for the week has been all about it. We've had lots of discussions in my lab and with the administration now. And I don't know Timnit personally, but I've been very impressed with her throughout her career and throughout this most recent event. Her courage, her willingness to be vulnerable, her willingness to speak what she believes and stand up. And I'm so grateful that there's women like that can be role models. to me, to my daughter, and to everyone. I'm optimistic that we can use this to try to redouble our efforts. And I think one of the things she's really taught me through her work is that outcomes are incredibly important and processes are incredibly important too. And we need to change both of those. And hopefully we can take this opportunity to redouble our efforts to fix these things and get better together. John?
Yeah. Okay. So it's really, really a pleasure to introduce Mazviita Chirimuuta, who I actually knew, not personally, but had been reading actually for longer than I realized, because she wrote this really incredible book about color that came out, I don't know, maybe 4 years ago or something like that, which is extremely good. Because color is one of those really weird things, right? And I've always been a bit afraid of it, but this book just was so great because it was neuroscience and philosophy, and it's just really good book on something that you think you've thought about, but I can assure you you haven't, right? So I knew about that book, and then I forgot. And then I heard you on Paul Middlebrooks, which was really great. I think you handled him really well. And that was really very interesting. And I read actually the paper before, and so I thought you'd be perfect for the Salon and get a chance just to very selfishly get to talk with you about all your great stuff. Just to do the sort of credential stuff, I got the institution wrong, but Mazviita is now at a senior lecturer at the University of Edinburgh, but before that was a tenured professor in the Department of the History and Philosophy of Science at Pittsburgh. She is double trouble because before that, she also had a PhD in neuroscience from Cambridge. So you can sort of see why that book on color makes sense, because it's very interesting philosophically and neuroscientifically. What we're going to be talking about today, I think, isn't color, but more about sort of analogical thinking about the brain as a computer and how far can we go. That's been a topic that we've discussed quite a lot. We had Marcin Milkowski on about a month ago, I think. I'm not sure if you had a chance to hear that, but there you go. This is a great topic. You've written very interestingly on this. I'm sure there are going to be strong opinions, and we very much look forward to your talk.
Okay. Well, thanks very much, John, and everyone for inviting me on. No, it's really an honor to be part of the Learning Salon and having this new and large community to talk to you about all these ideas at the interface of philosophy, AI, and neuroscience. So yeah, this is a philosophy talk. Should I go ahead and share my screen? Okay.
Scary screen sharing moments, but
yeah, let's see.
Yeah, there we go.
All right,
okay.
Let me play that. Okay, I guess once I share my screen, I'm not seeing anything from you, so do I still hear you? I can hear you, yeah?
Yes, can you hear us?
Say something, yes. So if something goes wrong and my visuals disappear, just let me know.
Right.
Yeah, so this talk is one of those, old nuggets. Is your brain really a computer, or is talking about computers and brains just the metaphor? But I think the deeper issue is that it follows on, very nicely from Martin Milkowski's talk at the Learning Salon, which is about this philosophical position known as computationalism, which is the view that cognition is essentially computation. And by taking this route through the philosophy of science and examining analogical reasoning in science, I think we can make a case for an anti-computationalist position. And the inspiration for this work is very much from that tradition of continental philosophy, which, if you've read anything by Hubert Dreyfus, What Computers Can't Do, he was drawing from that tradition himself. But he was not focusing on the philosophy of science dimension to these people such as Merleau-Ponty. And I think there is a sort of neglected argument there from thinking about abstraction in science and the limitations of abstract models to embodied cognition. So I'm just mentioning this different paper which really spells out this what I think is neglected argument from the history of philosophy. And yeah, and my piece today is certainly indebted to that tradition. Right. So yeah, the first part of this talk is about computational explanation in neuroscience. And what I'm arguing for is that the role played by the brain-computer analogy is one of simplification. And I'll tell you what that means. So it's a very commonplace thought about models in science that they contain abstractions and idealizations, like this joke about the physicist positing that a cow is a sphere floating in a vacuum. But when neuroscientists, assume that there are spherical neurons with uniform excitability, we see that these kinds of simplifying assumptions of abstraction and idealization certainly have their role in neuroscience. And I think, computational modeling can be interpreted very much in this tradition. So when you take the anatomy of the human brain and all its details, or this could be a mouse retina, and people are doing all this connectomics and like dense anatomical reconstructions on it, you'll see that there's this terribly tangled web of interconnections. But when you interpret these anatomical structures as neural networks, it gives you this quite handy simplification of saying that, well, all a neuron is an input-output device. So the dendrites are simply receiving signals. There's a weighted summation, and then there's an output. So you can abstract away from all of those messy biological details by taking that, by construing something like this slice of neurons as a neural network like the one schematized here. That was an image from a classic paper by McCulloch and Pitts, 1943, where the idea of neural networks and neural network computation was first introduced. And in a book of essays about McCulloch's work, the AI figure Papa talks about what he says is the liberating effect of the mode of thinking of McCulloch and Pitts' theory, because it eliminated all the consideration of detailed biology of the individual cells, and it really eased the problem of understanding the behavior of the nervous system. So by postulating that there is this hypothetical species of neuron defined simply by the computation of an output as a logical function of a restricted set of inputs. So in the paper that I shared, I go through a few historical indications like that. Another one is thinking about cybernetics and how people were building, early robotic devices like this one of Gray Walters, and using that as to get some leverage on what's going on in organic nervous systems. The idea being that if you build a machine which has some functional similarities with a behaving animal, and then you use your knowledge of how the machine is built to reverse engineer the animal, then that gives you some traction. Whereas otherwise, if you were just trying to look at the parts of the nervous system and try and figure out how it's built from scratch, you can just be lost in all the details. And this is a point made by the neurophysiologist Jerome Lettvin, also in that book of essays from McCulloch and about McCulloch. So, what he's addressing here complaints that were made against PDP, an early name for neural network, and connectionism. So people were saying that these aren't biologically realistic models, and he's saying, well, just having a artificial device that works gives you so many clues to where to look for in the nervous system to explain structure-function relationships. Right, so that's the background. This is this claim that, the big selling point of computational explanation in neuroscience, or the computational framework, or in other words, the fact that people build computational models of the brain, the real selling point of that, or the real use value that it has in the science, is that it affords this abstraction, specifically abstracting away from all of these messy biological details and considering the the operations of the nervous system just as these relatively simple neural networks. So this leads to the question, so does it mean that your brain is actually a computer just because computational models in neuroscience have been so successful and it's the dominant theoretical tradition now in neuroscience? And I argue that we shouldn't think of brains as literally computers. So the view that I defend in the paper is what I call the analogical interpretation of these models. And I contrast that with a literal interpretation. So I'll say a bit about this comparison in the next few slides. So on the literal side, what people are assuming is that the brain is a sui generis kind of computer. So not the same thing as the laptop that I'm running now, or literally the same as any man-made device. So sui generis, it's a distinct kind of computing system, but it's a computer nonetheless. It implements some abstract computations. The idea is that the models work in neuroscience. By that, I mean that they have predictive value, they get some explanatory traction, so they work because it's claimed they're approximately true representations of their neural targets at some level of abstraction. And this is quite a high level of abstraction that we're thinking of here. And it comes tied together with this philosophical position, which I called computationalism before, which is the idea that cognition is essentially computation. And I've heard discussions on the Learning Salon before about functionalism, and this is definitely connected with the functionalist theory of the mind-brain relation. So which is the idea that mental states are functional states of a computing system. So I don't think that's the right way to interpret computational models in neuroscience. So my own alternative one is just saying that the brain resembles a computing system in some specific way. So saying that there are some narrow functional equivalences between neural systems that are associated with particular tasks or behaviors, such as object recognitions, and computational models, including artificial neural networks, which can do, if you like, similar tasks. I think resemblance is somewhat in the eye of the beholder. I'll say a bit more about that in a moment. The idea then is that computational models work because they cut down the complexity of their neural targets to some humanly manageable size. So I'm not assuming that, the success of the model, if you like, their predictive value, their explanatory value is prima facie evidence for their being true, accurate representations of what is actually there in the brain. And then on the philosophical side, so I'm departing from computationalism. I'm not going along with this idea that because we have neural computational models, we should think that cognition essentially is computation. So I'm going to reject functionalism, but at the same time, I'm not going to embrace this reductionist view known as identity theory, which says that mental states reduce to neural states, and this idea that everything that, and this reductionist view that, everything that is to be discovered about the brain will have to take place at looking at the detailed neurophysiology. So I'll say more about alternatives both to functionalism and identity theory at the end. There's time. Okay, so this is another comparison between these two interpretations. So on the left-hand side, you have this view that there is just a genus of different computing systems. So the species in this genus have different kinds of physical realizers. So in electronic components and mechanical components, like Babbage's machine from the 19th century, or you could have a meat machine in which the substrate implementing the computation is nervous tissue. On the analogical interpretation side, what I'm saying is that neuroscientists perceive there to be a similarity between what's going on in brains and what's going on in computers, but that analogy should not be taken to mean a homomorphism or isomorphism. In other words, that there is some precise structure that is shared between those two. Reason for that is that once you go down that path, on most theories of computational implementation, that's like a long way down the road to saying that both of those systems are implementing the same computation. So that's why I resist reading analogy as just meaning that there is a precise structure that is shared across those two systems. And also, just to make it clear, I'm not talking about analog computation here. So another way to compare these two, on the literal side, there's this notion that computations are these abstract formal structures that mathematicians think about, originally invented, and that they map onto the causal structure of concrete objects. So in other words, that there's this implementation relation between an abstract formal computation and a physical device implementing it. On the analogical side, sure, there are these formal structures that mathematicians and other human beings have think about and write about, and computer engineers like engineer physical systems to implement them. That's all fine. But I'm saying when we're talking about brains, these abstract formal structures are no more than like a lens through which people are interpreting these neural systems. So that they provide a lens through which to interpret these data sets derived from experimental investigation of the actual brain. So this interpretation is drawing from some old work on analogical reasoning in science. So Mary Hesse was one philosopher of science who paid particular attention to analogies in science, because she thought that all scientific models were based on analogies between some system. It could be a machine, or it could be an observable phenomenon in nature, some system which is relatively well known, relatively well characterized, and then an analogy target which was not very well understood or not very well known, and people are trying to make sense of what's less well understood by drawing comparisons with what is familiar and well known about. So in this kind of toy example about trying to infer by analogy whether or not there's life on Mars, that's not a great case of scientific reasoning, but one that I find quite instructive, thinking about, you know, how scientists might have originally got traction of building models of unobservable phenomena, is to think about a case of analogical reasoning like that. And this is also one that I've got from Hesse, where her account of how the wave models of sound and light got started was through people's observations of water waves and people's noting of a similarity in some phenomena to do with sound, such as reflections and as in echoes and diffraction. And so the hunch was that you could use the same formal system to account for wave propagation of observable things as you could to account for unobservable waves, which are then posited on the basis of these analogies. So I'm using this sort of framework of thinking about scientific reasoning as analogical to make sense of what is going on in some classic work in cognitive science and neuroscience. So I take Marr, very well known for his 3-level framework and really promoting the use of computational explanation, saying that we should begin with at that computational level. And his work is very much influenced by ideas from the AI of his time and reverse engineering ideas. So the task that, you know, the computational models and the retina are taken to have in common is edge detection. And he built a model sort of for doing edge detection, this Laplacian of Gaussian filter. And by drawing comparisons with, you know, the behavior of the model to the physiology of retinal cells, he sort of put forward the Laplacian of Gaussian function as a model for retinal cells. And he was a literalist about computation. So he thought that there's reason to believe that, you know, these retinal cells really are computing this function. And so he's making these comparisons between the outputs of the model and the neural traces. And you can see that there's this nice visual similarity there. It's part of the case that he's making for this as a good model for biological edge detection. So departing from what Ma himself said about this work, I think we can fit this into this framework of analogical reasoning by saying that, sure, there are these similarities observed between the behavior of the model and the behavior of these neurons. There's also some observed dissimilarities. This symmetry-asymmetry thing I'll say more about in a moment, but this very important observed dissimilarity is that about the substrate of these two systems. So one of them is implemented in a digital computer, the other is an electrically excitable cell. So a similarity that is inferred, well, I think what this warrants is this more tentative inference that the neurons can be modeled as computing this Laplacian of Gaussian function, but that's as far as it goes. But I think importantly, Ma made this subtractive inference, and I think this is, if you like, the cash value of this computational framework, this subtractive inference that the differences in implementation are not relevant to the function here investigated. So this is what's sort of warranting this forgetting about all of those messy biological details. If you can show that there is a machine that does all the same things without having all of those same details in place, then you've got this license to ignore tons of complicated biological details and just go along with this modeling program in a more straightforward way. But an objection might be raised from a computationalist who's more inclined to this literal interpretation, which is to say, well, doesn't the model work precisely because the same structure or pattern occurs in the model and in the neural responses? So going back to this idea that the success of a model is reason to think that it's capturing something essential that is inherent to the system that's there in nature. And the reason how I push back against this, and the reason why I don't think that's the whole story, is that I think at the end of the day, what we call structure in neuroscience has a large element of investigator, not willful choice, but there's always some latitude in what gets counted as structure, because, you know, neural data are very complicated. There's always decisions to be made about what's signal and what's noise. And in the case of Ma, you'll notice in the neural traces that there's this asymmetry in the peak response, depending on whether the neuron is seeing an edge which goes from light to dark or vice versa. And it seems that in ignoring this asymmetry, Ma is treating this feature which is there in the neural data as, you know, not relevant to the explanation of edge detection. Maybe he thought it was just noise, or maybe he thought it was just a complication that wouldn't make his model work better. If you look at the papers from which those neural traces were taken, you'll see that the asymmetry is even more striking than comes across in the selection taken from Ma. So the point is that, you know, neural data sets are very complicated, and we shouldn't just assume that whatever structure is captured in the model is simply a structure which is there in the data, so much as a pattern which is suggested by the data set and somehow, you know, combined into what will fit nicely into a model. So this slide is supposed to sort of emphasize this point. So on the right hand side, I'm saying with the analogical interpretation, there's this notion that, you know, the brain has a set of characteristics, or that there are patterns that one can read off from looking at lots of neural data, and, you know, a computer model will have certain characteristics. We shouldn't assume that those just by themselves, that there is a subset of overlap there, so much as by doing this task of building models and finding functional equivalence, what the neuroscientist is drawing from both sides is what I call an ideal pattern, something which is suggested by the brain and and representable in a model, which facilitates making this brain-computer comparison, and therefore it facilitates this process of abstraction from messy biological details. And this can be contrasted with the literal side, which is just this view that the brain and the computer model will have a intersection of shared characteristics, a shared structure in common, which is the computation that both are implementing, and what's not shared is just the substrate, just the physical implementing device. Right, so what I'm gonna just talk about at the end is that, yeah, where I'm going with this research is that I think there are some interesting implications here for how we think about what's going on in artificial intelligence, and whether, you know, systems like AlphaGo are on the way to general human-like intelligence in virtue of the fact that already they are capturing something which is essential to human cognition. So I think these ideas about, you know, the path towards generalization and becoming more human-like in more and more respects, sort of resting on this computationalist philosophical idea that, you know, by capturing what computation is going on in the brain, then you're getting to what you're distilling what's really the basis of intelligence. But if you don't buy into that idea, then you're left with this view that, like, you should no more expect a descendant of AlphaGo to one day be like HAL in 2001 Space Odyssey, my one sci-fi reference. We should no more expect that kind of transition than we'd expect, you know, a car to one day, in a few generations of technology down the road, to start spontaneously being able to leap over logs. That's because, you know, pulling, you know, what a car does and what a horse does is one simplified kind of motion that cars were engineered specifically built, but no one thought of cars as, you know, doing something which was somehow essential to biological motion. They just do one task that animals can do, and they do it really well, superhuman performance. But then there's loads of other things that animals do which cars are not built to do. And there's no reason to think that by just having one kind of technology and just scaling it up or making it more powerful, that you would increase the range of that biological similarity. Okay, and I put in one slide, it's something that's not covered in the paper, to make the point that rejecting functionalism doesn't pull you back into that bad old reductionist theory. It's a bit of an arcane point. I don't know if it's worth going into this now, but I would say one of the reasons that functionalism's been so appealing in the philosophy of mind is that it allowed you to say that there's more to neural systems and minds and creatures with minds than just, you know, the aggregate of neural activity, that there is some, if you like, higher level form or structure which almost has a top-down influence on what else is going on. So it's quite an anti-reductionist view. And so it had this appeal as an alternative to this mind-brain identity theory, which is ultimately saying that all you need to know about the mind will be conveyed just by looking at the nervous system and individual neurons ultimately. But I think that if you take the embodied cognition view seriously, or, you know, you can get to thinking about that. You can be both a anti-reductionist and someone that believes in, you know, higher level organizations, in living systems as a real thing. So one of the reasons for thinking this is that the embodied cognition view is just quite suspicious of overgeneralization from properties of artifacts to properties of organisms. So one thing about artifacts that people make is that there is a clear, you know, matter versus function or structure, organization distinction. So we have this clear intuition when we're building things that you can take the same material, like this bronze, and mold it into different statues. Similarly, you can take, you know, the same material and create all kinds of different machines with it. Likewise, you can take the same design and make it out of different kinds of materials. So this whole idea of multiple realizability or substrate independence, I think, is very much tied to this intuitions that people have about building artifacts and making machines. A consequences of view that I'm proposing and why it's sympathetic to embodied cognition, I'm saying that, you know, we shouldn't buy into this substrate independence or the strong form of material multiple realizability, this idea that you can implement a biological mind in all kinds of different material systems, because I think that's too much tied to this intuition about artifacts. But at the same time, you can think about, you know, high level organization and material substrates and living systems as being very much interdependent, and that there are different kinds of properties of living systems like robustness and degeneracy, so that you can have the same biological function carried out with, you know, slightly different material bases, because that's what conveys robustness, but that's just not the same thing as substrate independence, right? So we shouldn't be thinking that just because in living organisms there's a certain amount of independence of form and function and material organization because of degeneracy and robustness, we shouldn't be compelled from that to thinking that material implementation doesn't matter at all. But at the same time, because there is this robustness and degeneracy, that is itself a reason to say that, yes, it's important to look at function and organization and not just think that all of the explanation will have to come in that bottom-up fashion. Okay, so this last slide, go into some conclusions. So computation is not assumed to be the essence of biological intelligence on the interpretation that I propose. I'm saying that we shouldn't extrapolate beyond narrow functional equivalences to thinking that you have explanations of some cognitive capacities more generally. I think it's important to consider whether disanalogous features, the details of neuronal substrate or context within the organism, so both lower level, if you like, different disanalogies and higher level contextual disanalogies, whether they do matter for capacities beyond these narrower functional equivalences. And I finish with a line from the neurophysiologist Lord Adrian, which is, what we can learn from the machines is how our brains must differ from them. Okay, thank you. Okay, so that's it.
Thank you so much. We are clapping virtually.
Okay, sure. Yes, just let me escape so I can stop sharing my screen and then I can see people again.
Of course, you can. Okay, you can stop sharing your screen. One of you has a loud noise. I think. Is it Jovo?
I have some loud noises.
Okay. Okay, so who wants to go first? John, is that?
I'm totally open.
I can't hear you now for some reason. Oh, now I hear you. You had a delay.
It's totally up to you, Ida.
Go ahead. Why don't you take the floor first? And everybody's clapping hands for you. I know you. Okay. I don't know if you can see the chat now.
So I actually, thanks for that. I think Ida and I consider ourselves functionalists. And I've always thought of functionalism for us is more about whether one is allowed to think about psychology and cognition somewhat autonomously from circuit level neuroscience. Okay, so in other words, that's one thing, which I think isn't necessarily implying some obligation to the computer-machine human mapping. So it seems to me, and then The other thing I feel is that I find it a little bit difficult to know the difference between idealization. So, for example, when Hodgkin and Huxley in 1952 had differential equations, a circuit diagram. So there was the visualization of a circuit diagram with capacitors and resistors in it, which clearly we don't think that the squid giant axon
Right,
has
sure.
resistors and capacitors in it like that. And yet the abstractions of resistance and voltage and change were correct. So I can't tell whether analogy is different to idealization when, for you, when somehow you have two systems that are literally in existence but made out of different substrates, like computers and brains. Whereas if I'm thinking about a squid giant axon in terms of circuits, it's not like I'm saying that the squid giant axon is literally a circuit made out of rheostats and capacitors. So I can't quite get my head around when you think it's been overstepped. Whereas in the Hodgkin and Huxley case, I don't think you'd have an objection to them idealizing with a circuit. So I can't quite get the difference. What am I missing?
Yeah. So just on that first point, I mean, functionalism, if you define it as a view which says that there are, the science of autonomy, psychology is relatively autonomous from neuroscience, that's not inconsistent with anything I said today. And those last points about how, taking the embodied cognition view can also warrant that kind of position if you just allow that there to be sort of emergent organizational patterns, and that's consistent with that. As to where the overstepping comes in, so that I think of this project as, really, why use this word interpretation? I'm not saying that any of the models themselves in science, neuroscience, should change or be done differently, but it's really about the question is that, the science is coming up with all of these models, and how should we, especially as philosophers, interpret those? And it's similar to questions that people had about, interpretation of theories in physics. So when a physical theory posits certain unobservable particles, should we as philosophers take on ontological commitment to those unobservable particles? So it's an issue in that line. So the science is there. What is the significance for it for a wider philosophical view? And so a particular wider philosophical issue is whether cognition essentially is computation, whether your brain is a computer or if it's not. So with the Hodgkin and Huxley, I think that, that's a really nice case of analogical, model building via analogical reasoning. So importing ideas and concepts that come from one domain, so electrical engineering, and just putting it into another. In biology, I don't know enough about what Hodgkin and Huxley were saying about those components there, whether they're saying that the resistance of the capacitors was a way of describing in aggregate some properties of the cell, or so this was just like a symbol for the electrical resistance of the cell, and certainly a cell has this property of electrical resistance, so you can just label that as, give it the symbol of a resistor. But I don't know more about the details.
So why couldn't? So that's exactly right. In other words, there's the material difference between a circuit that has capacitance and resistance versus a membrane that has differing degrees of it based on its voltage sensitivity. But in terms of notions like resistance and capacitance, those are common to both systems. So if I said, instead of the C word capacitance, I said cognition or computation, why wouldn't I be allowed to abstract up that commonality, even though I accept that at some lower level they're very different? And I was on a meeting earlier today about dynamical systems, and I was very much taking the Marchine view that in the end thinking about cognition without thinking about computation or representation seems quite difficult to me, right? And I gave the example today of the word facetious. How many vowels are there in the word facetious? So you have to picture the word facetious in your head, and then you have to operate counting the vowels until you realize there are 5 in facetious. Now, I just don't know how to explain that act of thinking of the word and counting the number of vowels in any other way than computation and representation. So in that sense, computation seems to be a perfectly valuable abstraction, just like capacitance is a perfectly valuable abstraction, even when the substrates are entirely different.
Yeah,
so what am I missing?
So I think the difference there is I wouldn't call the Hodgkin-Huxley thing with resistance and capacitance as an abstraction in the same way. Certainly, they're looking at some aggregate cell properties, and they weren't looking at individual channels or anything like that. But you know, resistance can be just defined as voltage over current. So it just is a property that you can measure of a piece of wire or a cell membrane or a piece of wood, all kinds of things. You can just measure the resistance. So there is no like core notion. It's not like the notion of resistance is actually tied to a particular kind of physical material. It's just those ideas were developed more maybe in the context of people building things with electricity, but maybe it was just the basic physics of electricity. I don't even know what the background to that is. Whereas I think, you know, defining computation and saying which physical systems have computational properties is actually a much more unclear issue, a much harder question. So there's this whole literature in the philosophy of cognitive science about triviality worries about implementation, because if you say that all it counts to be implementing a computation is that there is a mapping between physical states of a system and some formal structure, then people have argued, well, you can say that anything like a rock is implementing the same computations as your mind. And so this has actually been like a long-standing problem for the computational theory of mind, is actually specifying, okay, what do you mean by implementation, such that you can say that your laptop and your brain are implementing specific computations, but not anything that we say is non-cognitive is implementing computations. And this is a not easy to answer problem for the foundations of cognitive science.
I thought the way out of the triviality argument was that you have to bring in a strong notion of representation. That there is no computation without representation. Turning Fodor backwards, right?
Yeah.
That the way out is to say, you could do that sort of thing about a rock, but once you say cognition really needs I representations in order to compute on, you can escape that trap a little bit, it seems to me.
Yeah, so that is one way that people have gone. Orange Chagrin is someone that takes that line. People worry about it because there are perfectly well-defined notions of computers that don't have any representation. So are you going to rule those out? That was all.
Yeah. Well, yeah, it's extremely interesting, right? How when are you allowed to have because, you know, resistance and capacitance, you sort of were talking about them as though they can be substrate independent notions, right? That you can write that equation out for any substrate. So it just seems to me, by analogy, that you could talk about computation being cognition being somewhat substrate independent when you think about it as computation over representations. So I find myself, you know, and I'm sure it seems to me, at least from the psychology versus neuroscience autonomy argument, it seems like you would be a little bit more, based on the way you've constructed your argument, more sympathetic to the functionalist autonomy argument, right?
Yeah.
Yes. Yeah. Right.
Yeah, to the extent that it's just an anti-reductionist view. But I think there's more ways to be an anti-reductionist than to be a computational functionalist.
A computational functionalist.
Functionalist. Yeah, to say that, you know, minds are completely substrate independent and therefore realizable in artificial devices.
Well, it's interesting. Well, I will stop there so I don't hog you as much as I would like to, and whoever's next.
So maybe I can follow up on that if that's okay. So first of all, thank you for the wonderful talk. I was, oh, that noise was John's.
Okay.
So I was very happy to see, especially your first slides and the books that you had there. I think that it's not every day that we see Gangilem in a neuroscience talk. So something that I am confused about is that, as a matter of fact, what I understood, and correct me if I'm wrong, is that token identity and not type identity is in fact consistent with functionalism. It's not the identity, the type identity theory that has a problem, but not the token identity, which says every single mental state is identical to a sort of a token of a physical realization. So first, I wanted to say that there is a way in which, in fact, token identity and functionalism they go together. And also, if we're not doing at a type identity level, either in function or, you can think of token functionalism also, which is the same as something you wrote. You wrote at some point that there is a functional equivalence for specific tasks, and that is functionalism. So in a way, I think I was a little confused because it seemed to me like you're presenting a version of functionalism that is consistent both with token identity and with functionalism. But then you're saying that it's anti-functionalist, or you're saying that it's against multiple realizability. And I'm not sure if I understood. I didn't understand why multiple realizability was challenged. I didn't understand why token identity would be inconsistent with what you said. And I also didn't, because token identity is the minimum for not becoming a dualist, right? And then the other thing I didn't understand was why functional equivalence for specific tasks isn't also functionalism.
Yeah.
So if those three,
so I'm using this word, functional equivalence, just in my own way to say that what people are doing when they're building these artificial devices is they're taking something that an animal can do, or a part of a brain can do, and creating an artificial system which, for specific operationalizations of this capacity has an equivalence, right? But that's not to say any more than that. It's really sort of narrowly confined to, certain operationalizations like core object recognition, whether you can classify an image thrown up within 100 milliseconds, something like that.
And if I may ask very shortly, sorry for part of the interruption, just
because functionalism is a view about the ontology of mental states, which is to say that they are functional functional properties of systems as opposed to material properties of systems, or as opposed to non-material properties like a dualist mind. So just talking about functions in the way that I'm doing doesn't entail anything about the ontology of mind. I'm just saying that you're building something which does something similar to another thing, right? But that doesn't mean anything about the inherent nature of how either one of those does that thing. So it just means that they have, on some benchmark, they have a behavior in common.
So, for instance, the famous example of pain with C fiber in mammals versus pain without C fiber in octopus. It's pain in spite of the fact that the substrate is different. Therefore, we can think about pain as a function. Is that something that would be acceptable as a function in your category?
Yeah.
The idea of
so pain. So that's one of the old long-standing arguments for functionalism against the identity theory was that the identity theory, because it reduced pain to C fibers twitching, couldn't allow you to say that something with a different nervous system without C fibers had that same mental state. I don't think what I'm talking about here has any specific standing on whether you could ascribe the same mental state to different kinds of animals with quite different nervous systems, because the view that I'm proposing here is that there's enough of a difference between what's going on in the substrate of digital computers and any man-made machines and living tissue, biological brains, that we should be wary of thinking that they really are, that these devices that we've made really are doing something which is essentially cognitive, and that we shouldn't be like misled by these quite narrow analogies. But that doesn't mean to say that in living systems that there aren't, you know, functional profiles, if you like, which are somewhat free floating of the actual nitty gritty material realization. So, you know, I wouldn't want, I'm not going down that path, which is so reductionist that there would be worries about, you know, me and someone else with, you know, different neural organization sharing the same belief or having the same mental state. When you're talking about humans versus octopuses sharing the same mental state, I think that's so hard to say anyway that I wouldn't know what to say about that. But no, roughly speaking, you'd want to say that all different animals have pain states, but maybe that's because I'm thinking of pain states as something that isn't really that really is quite a concept which is quite autonomous to psychology anyway, and maybe it's not like the neuroscientific concepts really matter to me when I'm asking what creatures have pain.
So just so I understand, what would be the benefit of this perspective, either for understanding mental states or for understanding neuroscience or for developing AI? So what would be the difference between holding your analogical position versus a functionalist and token identity, which actually go together? What would you think would be the difference in the science that would be thinking like this versus the other?
So the view on the ontology of mind that I think is most congenial to what I'm saying here, though I don't explicate it or adequately defend it, is I think this embodied cognition view, and that's where I'm, you know, that's where my heart is right now, which is this idea that what cognitive systems are is somehow deeply tied to what it means to be a living system. So Peter Godfrey Smith is one philosopher who's been pushing this recently, and I'm quite sympathetic to that. Also, Evan Thompson is someone else, and if you want to like go right back, it's really an Aristotelian view. I think it's much more deeply Aristotelian than functionalism is, even though people say that Aristotle was a functionalist, and I beat up a bit on Aristotle in the paper. But yeah, I would say that that's ultimately the kind of view about the ontology of mind that I would like to defend. And so and computationalism or computer functionalism is one view that gets in the way of that. So that's why I'm presenting reasons why, just to say that even though the computational framework is the dominant one in neuroscience and cognitive science, that doesn't give you reason to think that cognition is essentially computation, because that's the position which is incompatible with that embodied cognition view. So I guess there's more of a philosophical motivation than thinking about what would actually bring progress to neuroscience, because I'm saying, yeah, neuroscientists should carry on building computational models. It's a useful abstraction. I think there are warnings about being so taken in with this computational framework that you miss other properties of nervous systems which would be more salient from a different perspective. So I think multiple perspectives are actually needed with something as complicated as the brain. And then with AI, that's where it becomes a bit pessimistic, because I become doubtful that you can capture what's really intelligent about living systems in these machines which aren't living. So I generally think that, understand, all of these things that seem really problematic, like understanding, agency, consciousness, even common sense, my hunch is that they're much more tied to things that creatures have because they're alive than people have thought about so far.
So here is a challenge I'm facing now, even from the philosophical perspective. Right. So I'm an avid reader of Peter Godfrey Smith, Evan Thompson, also Francisco Varela, and earlier embodied cognition people like Al-Noé. As I studied, sort of my graduate degree was with brilliant school of mind and brain, you always had one
Okay.
advisor that was a philosopher and
Right.
one that was a neuroscientist. So we read a
Right.
lot and talked to these people because they came
Yeah.
and visited a lot.
Mhm.
So here is the challenge I'm facing right now.
Mhm.
So in AI, there is the notion of affordances, for instance. Gibson has, and the idea of embodiment and sort of
Right.
embodied cognition, a lot of those ideas have actually made it to AI.
Yeah.
I don't know if it is necessarily the case that embodied cognition is inconsistent with all notions of functionalism or with identity, or with token identity, for instance. It could be various tokens if you have, like, you know, it doesn't, if you have multiple realizability, you can have various tokens. And also, I'm not sure. Yeah, so that's where I think I'm a little even
Ida,
philosophically confused. Yeah, go on.
Ida, can I ask you a question? I mean, I'm sorry, Jovo, but I think I'm beginning to understand, and I mean this in the nicest way. I think you've now, through your conversation with I understand your agenda,
Okay.
right? Which I think, and I think what's going on here, as I'm beginning to understand, is you're not so troubled by an octopus versus a mammal feeling pain, and you haven't really gone after the functionalist arguments for the autonomy of psychology and neuroscience, because what they have are bodies and life, for lack of a better set of words. And what you're actually saying, I think, because of that life, body, Peter Godfrey Smith sort of post-Cambrian explosion view, sort of that, I see where you're coming from, because if it were not analogy when it came to actual machines, in other words, it wasn't analogy, it was literal, and they don't have bodies for the most part, despite what Ida's saying is happening, but let's just for the time being, you know, AlphaGo is not a body, right?
Yeah.
Then your position on needing life in a body and the Peter Godfrey Smith, Alvanoe whole view would fall apart a bit, because so I now understand where you're coming from. Now, it may well be logically true that when it comes to machines and humans, it's analogy. And when it comes to animal and animal, it might not be analogy. There may actually be functionalism of the kind that you probably could live with.
Yeah, or genuine commonality.
Genuine commonality, right. And you have evolution on your side for that, right? To some degree.
Yeah.
But I do sort of see that there's no a priori logical way to get that divide, right? There's no definitive way from argument, if I understand it, to say I'm okay with an octopus being true commonality, but a machine is pure analogy. There's no slam dunk, is there?
Yeah, so no, not in, you know, what I've presented here today. I mean, one of the things I'm researching at the moment and I'm very interested in is old arguments for the autonomy of biology, because I think once you go down that route, you're allowing yourself to say that there are, you know, things that come in with living systems which are just not characteristics that are available in non-living systems. So yeah, that's part of the interest in Canguilhem and Goldstein and people like that. Yeah.
So it's an interesting maneuver. Yeah.
Okay.
I mean, I think I'm sympathetic to the idea that I wouldn't say that the brain is literally a computer, but I do think that there can be functional equivalence between some computation in the brain and some realization of a similar, let's say, operation. And that can be operationalized, task specific, as you were mentioning, and function specific. And it can be realized either by biological neurons or in silico. I think that the main idea that you have that, hey, we could have other things that we would say. I think an example that a couple of sessions ago I gave was that imagine a thought experiment in which we all were obsessed the way we were obsessed with computation. We were completely obsessed with, let's say, navigating oceans. And then we might be arguing that the brain is literally navigation or something, or the mind is navigation, right? So while there is, again, now I'm going meta, multiple realizability of
Yeah.
what the brain could be functionally equivalent to. I do think that if one can draw that functional equivalence, and if there is, especially if there is common math and common behavior in it, there is the possibility of drawing those functional functional equivalence, in spite of the fact that we're not saying. So let me put it this way. I can say the brain is like a computer without saying the brain is only a computer. I think maybe that only is the key where I'm sympathetic to you, that I wouldn't say it's only that. But I think I might, but somehow I'm still a functionalist, and also I think token identity theory is consistent with this and makes sense. And I'm also a fan of the embodied cognition. So that's where I'm trying to figure out now in the sort of the multi-dimensional state space of embodied cognition, token identity versus type identity, functionalism versus anti, which quadrant we are.
So I certainly agree that these ideas from embodied cognition are having an impact more widely, but I think there are parts of the fully fledged embodied cognition idea which are just not compatible with, machine intelligence. And in that historical paper I mentioned, I was making that point that, why Merleau-Ponty himself was so resistant to cybernetics, and he just thought that was a misleading path to go down in terms of using that framework to understand human psychology. But also I'd like to say that, there's something special, I think, about the computer analogy, just because of all the machines that have been built, all the technologies that have been built. Computers are the one thing that were purposefully designed to replicate a kind of cognitive work that human beings do, like just doing loads and loads of arithmetic and then building from there with AI and more different tasks. So I think there's something. So the reason why the computer analogy grips us is because it's a machine that was made to replicate us. And then we're using it back in a loop to try and understand ourselves.
I appreciate that. Just one last thing before going to Jovo. So Francisco Varela is one of the earlier people in embodied cognition. And he was, very into the math of it all and explaining things in the dynamical systems version of things. So would you be against that kind of a perspective too? Because it's using math as the thing that captures the embodied cognition or in that dynamical system that's living?
Yeah. So I haven't read enough of Varela's work himself to really say much about that, but it's interesting, that there's this connection with autopoiesis and everything. In the paper I wrote on the history, I think there is an argument there in those guys, especially Bergson and Husserl, that actually, using too much maths to try and understand living systems and lived experience would be missing out something important. So that worry about imposing abstractions, I think, could include different kinds of mathematical frameworks, and that's an old argument from those guys. But yeah, it's not to say that you'd have to buy into that now, but I think it's interesting that that's a position that's out there.
Thank you so much, Jovo. Thank you for the conversation.
Thanks. Thank you.
I had 3 questions. Ida asked one of them. Jess Thompson has asked the other one and asked a question, so I'll let her do that one. And then I only have one left, so I'll just ask that. I'll just make a couple of comments first. I think, so I basically agree with what Ida is saying, that I think I am a computer, and I'm other stuff, like I'm a dad, I'm a husband, I have to chop wood, so I'm a wood chopper. And it's okay from my perspective to say I'm all those things, and I'm all those things at different times. And just from a math stats perspective, they're all projections onto like a relatively low dimensional space that characterize a part of me, and you're never going to characterize all of me. That perfect model of me is just me again, and that's not a very useful model. And kind of going along with George Box's all models are wrong, but it's okay. Like, they're supposed to be wrong. They're supposed to summarize a particular part of us and characterize it well. And it's supposed to ignore all the other stuff. That's what makes it useful, is choosing which things to ignore. So So that was one thing that I thought of, and then the other comment is, something that you said is kind of interesting, like what to do with this. It almost sounded like you said, if we're going to try to build human-like or biological-like AI, we should be focusing on robotics and like robotics AI. And so I'm a little curious if you really mean that, or if I just inferred it, right?
Yeah. Thanks for that. Yeah, so I certainly agree that a general point of interpreting models should be, realizing their partiality and that their use comes through partiality. And I think that's just a point that computationalism hasn't managed to follow through on. I think it's just much more committed to the idea that, the model isn't just, false and this partial representation, but it's more like the model is seeing through this surface complexity to some essential underlying simplicity. And I think that's the wrong way to interpret them, but I think that's an idea that's out there in, amongst philosophers of cognitive science, and sometimes I see it in, neuroscience textbooks as well. So that's one thing I'm pushing back against. And then with the robotics, so like I said, the view that I'm, most sympathetic to on philosophy of cognition right now is one that says that there's something important, an important division between living and non-living systems in terms of like dividing what can have minds and what can't have minds. So just a robot, something that moves and acts in the world, wouldn't get you there if what's critical for being a cognizer is like being something which is alive, and so that therefore having true agency, having true goals, and things that you need to really invested and need to keep doing in order to maintain yourself as being alive. So yeah, but there's definitely work in embodied cognition which takes this idea that just being embodied and having more of a close interface with the world, so perceiving and acting is needed for cognition. So if you take a computer which is not alive and but give it more interfaces with the world, that will give it more intelligence. It's a move that's out there. I'm not convinced that it achieved a lot, but yeah.
Okay, and so sorry, there's one more thing.
Yeah.
Before hopefully Jess is going to join us. Is that right?
Okay.
Yeah,
so,
you can invite her.
Okay, so my last question then is, it seems to me like a lot of what you're saying, in a sense, depends on one's stance with respect to scientific realism. Insofar as if I'm a hardcore anti-realist, then the literal interpretation is kind of nonsense.
Yeah.
And so is that right? And are you taking a strong stance on a kind of realism?
Yeah. So one of my criticisms of computationalism would be just that it's like uncritically just absorbed some scientific realism and just over. So one of those moves is to just inferring from the success of science that it's truth, and yeah, that a lot more debates over scientific realism need to be brought to bear on these debates about philosophy of cognitive science. So that's definitely something that's bothering me in the background here. I'm not going all the way to instrumentalism. I'm not saying that models are no more than a tool for predicting future data. With this analogy idea, it's a bit of a halfway house, because you can say that the model is giving you a caricature of how things are in nature, which is to say that it has a representational content, but it's not useful in virtue of being true, which is different from instrumentalism, which just says that there is no representational content to the model.
Cool. Okay, great. So
thanks.
Jess, welcome. I wonder if you would be willing to introduce yourself and then ask your question.
Sure. Do you hear me? Yeah.
Hi. Yeah.
Great. Yeah. Thanks for your talk. Yeah. So I just finished a PhD at the University of Montreal, interested in neuroscience and deep learning philosophy of science. So super excited for the learning salon in general, but also for this talk. Yeah, so I wanted to ask a question about kind of computational modeling outside of neuroscience and cognition. And sometimes I wonder if we have kind of two senses of the word computation, where part of what we want to do in science in general is come up with models and building right. scientific theories that are themselves models, and when those models are often computational. And in other domains, we don't have this kind of these conflicts about like, well, oh, is the digestive system a computer, or is right. this tornado a computer? So I wonder if we only almost have two conversations, whereas like one conversation about like what kind of models we want to build in science, and another question about what is cognition. And I wonder if like those are two separate conversations. Does that make sense? Or?
Yeah. So I certainly think that there is a different interpretation standards that are brought to bear when models are used to, computation is used to model systems with minds or parts of creatures with minds, like bits of their brain, than when it's used to model anything else. Because computation is just this universal framework for representing patterns in nature. But obviously when we're talking about hurricanes and I don't know, water waves or anything else, we're not importing like ideas about those things really being computers. So that's one sort of weird thing about interpretation of computational models in this domain. And so I think what's driving that is this background belief that in place, which is that computation is the best way to make sense of why some things in nature have minds and have cognition and some things don't. And so that's an antecedent philosophical view, which is saying that, our best bet of understanding why it is that there are minds in nature is to say that some things are computers. And hence when we find in neuroscience or cognitive science, scientists using computational models, that's taken as evidence for this, actually what was an antecedent view, which is that computation is the best way to account for the existence of minds in nature.
So would you then advocate for, when we're talking about computational modeling in neuroscience, that we treat it basically the same as any other type of computational modeling, that it doesn't have to imply these other considerations?
So I think, strictly speaking, it doesn't have to imply these other considerations. Though one thing I do think that maybe there is some pragmatic value of, amongst the scientists themselves, as reading things a bit more literally than I'm saying, strictly speaking, we should do, which is when we're using words like representation and coding, it gives us really handy vocabulary to make sense of neural systems, is to import some of that ontology. And this is something, another piece of writing that I'm working on, is how we should interpret representation talk in neuroscience, which is closely related to the computational framework. And I think that it does have some heuristic value to work on the assumption maybe that these things really are representing and computing maybe in a stronger way than you would ever say about a hurricane, because I think those terms pick up some of the distinctive things that are there in cognizing systems that you just wouldn't find in a hurricane or a bunch of water waves or something like that. So with representation in particular, the fact that neural systems are really sensitive and tightly controlled by stuff which is really distal to them, which is different from how more purely mechanical systems that you work. It's like this long range sensitivity, that all these intentional notions are a really handy way to capture that, and you just don't get that from other frameworks. So that's something I'm thinking about.
Thanks a lot.
So why don't you stages, and we have Jonathan Roski and Adam Charles, because David Finnell had asked the question that he asked, what is cognition if not computation? And Paul Chizek gave a response, which is the reference to this paper, what might cognition be if not computation? And that's by Tim Van Gelder, 1995. So do you want to add anything to that? What is cognition if not computation?
So I think the dynamical systems answer is just another framework or perspective that stands alongside the computational one. And it's interesting that that is as much based on a machine analogy as the computational one. So ideas like the governor, self-regulating machines, again, they have some nice similarity, something nicely similar in common with cognizing systems, but I don't think cognition is essentially what is captured in those dynamical systems theory models. So sorry, Paul, we have a disagreement on that.
So I don't know if David Finnell was here. Yeah, go on.
Yeah, that's another chapter in the going to be another chapter in the book. So comparing computationalism and dynamical systems as different perspectives on the brain.
Ah, great. And it goes back to the question about Varela, because Varela was the dynamical systems approach and not the sort of information theory.
Yeah.
All right.
So in my view, I'd love to hear it. It's a non-starter, I think, the dynamical systems view of cognition.
What do you mean?
I'm just saying, I think the dynamical systems, a non-representational view of dynamical systems, I'm saying is a non-starter when it comes to cognition. That's what I'm saying. So the Van Gelder view, and there are lots of people, right, that, from Bechtel and Kaplan and others who've said that you can certainly have representational senses of dynamical systems. Anyway, that's not the discussion for now. I think Jonathan was going to ask a question.
Yeah, hello. Can you hear me? All right?
Yeah.
Great. Okay. So hello. Great talk. I really enjoy reading your paper. I'm a PhD student in mathematical linguistics, and I also work in a neural dynamics center at Stony Brook University. And one thing that I was intrigued by in your paper was that you referenced McCulloch and Pitts to discuss like the merits of abstraction, which I loved. And it made me want to think, like, what is the right level of abstraction for sort of productively approaching these questions? And what it made me think of was, you referenced McCulloch and Pitts, but then you didn't reference Stephen Kleene, who had like taken McCulloch and Pitts and formalized them in order to, derive the class of regular languages, the finite state machines, even define the first recurrent neural networks. And like that was super productive. I mean, it's like a foundational result of computer science. But I don't think anyone would say like a regular language is a principle of neural function. Like I don't know that that's ever taught. Like so I'm just wondering, like that was productive, but I don't know if that, like, what's the right level of abstraction for us to sort of move beyond this sort of interminable debate of is the brain a computer, right?
Yeah. So I don't mention McLean because actually I don't know his work. So that's something. If I could get some references on, that would be great. So what the right level of abstraction is, I think that is the key, critical, essential question for neuroscience because the science of it will only progress by finding, if you like, the right level of simplicity in this really, really complicated system. And people have bet on computation being the right level of abstraction, but Lily, Krapp, and Cording have this paper about understanding neural networks, which is arguing that maybe computation isn't the right level of abstraction to explain the things that people have been wanting to explain. So maybe it's limited. Maybe there's a different level of abstraction, or maybe there's no level of abstraction in which everything is going to be really clear. Like the really tough nuts to crack, like consciousness, maybe it's because there isn't a right level of abstraction at which these can make sense. There's just, maybe you really need the details to make, maybe if where I'm going with this, if for systems to be consciousness, all of the details really do matter, then we're not going to get a level of abstraction in which we can have an interpretable model of a conscious system. That's what I'm saying. So I think these are very much open questions.
So do you think there might be types of abstraction that we might more productively consider? So for example, maybe a regular language is too insufficient. Well, okay, then maybe it's true that we should just look at all computable functions, or even non-computable functions. Like there's what's a description language for discussing this problem? in such a way that like we actually can sort of analytically pinpoint something, right? Like, is there even such a thing?
So I feel like this is a question that, you know, can't be really solved from the armchair by philosophers, but the only advice coming from the philosophy that I've produced is that people should be considering various things. So if, you know, computationalism as it's been thought of classically is just one level of abstraction, I'm thinking in particular of like the Carandini and Higa canonical neural computations, where they're saying, well, yeah, if you take a normalization model and then that's, you know, realized in different kinds of parts of the brain, then this gives us this nice level of abstraction, which you can explain a bunch of things. And the Lillicrap and Cording paper was saying there's reason not to think that. So the advice from what I'm saying here is just that people need to be trying all different approaches of how much they should abstract, maybe abstracting a little bit less, maybe a bit more, and not be too tied to a particular framework, because one of the reasons you can get tied to a particular framework is if you think it's really, you know, revealing some essential truths about the system, whereas I'm saying that it's not, because that's not the business that models really are into.
So if maybe here I'll make it more specific. If I get an analytical result, right? I mean, it's not, I don't need to approximate. I don't actually, you know, I can replicate it by virtue of, say, having a proof, right? Or something like that. Or I have some convergence guarantees or something. Like, that's not really truth. I wouldn't pretend that's anything true, but it's certainly verifiable. It's certainly analytic. And so, like, how, I think, like, that's what people are after when they, like, adopt the computational metaphor. But, you know, of course, they never get it, right? So, like, how do we guarantee these analytical results without sort of just adopting the cloak of computationalism?
So you're saying that it's a legitimate goal of the research to expect those kinds of analytical results, or like to be able to like prove theorems about how the brain processes information?
Well, you at least get certainty with them. I'm not saying it's everyone's goal, right? I mean, like the Hodgkin-Huxley example is great, right? Because we have governing laws. You know, there's certainly
So
not every squid is going to give you that, right?
Sure. So your question is, like, should people be trying for that, or what's the best way to try and achieve that?
Yeah, like what should the neuroscientists do if we're not trying to get these sort of analytical laws? I mean, you know, like, or like what are we getting out of the analogy?
No, that's a interesting question. I mean, so there are certainly like beautiful, elegant theories in neuroscience, but often when they meet the people that like know a lot of neurophysiology and neuroanatomy, then the complaints are that's a beautiful theory, but it doesn't apply to what's going on in the actual brain. So that's some warning in general about like theorizing in pursuit of what is analytically provable, that it often doesn't meet up with reality. But it's not to say that those kinds of goals shouldn't be pursued, as long as it's not at the cost of some other approach. I don't know what else to say there. I was listening to the interview on the Brain Inspired podcast with Jim DiCarlo, and he said something that actually quite resonated with me, which is that people had gone into neuroscience often with like a physics-inspired ideal of how science should work, which is that there should be beautiful, simple theories. And he thinks that his research shows that the beautiful, simple theories that you can just write down a few equations, then, this is capturing what's going on here. That's probably not going to work, because the truth about the brain is probably a lot more complicated than that. And so there's reasons not to think that the beautiful, simple theorizing ideal is going to work so well with something as complicated as the brain, given that the systems that physicists deal with tend to be a lot less complicated.
Wasn't
And I'm
that
just using that word complicated a lot.
wasn't that wasn't that sort of what the mechanistic turn in
Mhm.
the philosophy of neuroscience was, to get away from sort of covering law
Mhm.
views, which
Mhm.
was sort of a hangover from
Yeah.
physics, and that whole
Yeah.
neo-mechanists basically said that's just not going to work for us, right? It seems to be that was one of the incentives.
Yeah, that it doesn't capture scientific practice, which is that, you know, often what scientists do is they have their so biologists, so talking about in particular what biologists do is that they'll have this particular system that they'll study exhaustively and map a lot of mechanistic details without giving you an equation which sums it all up or predicts the behavior. That all you get at the end of the day is just the description of the mechanism.
But
Jonathan,
isn't that what we want from computation? Like, if I write an algorithm, that's basically me telling you exactly what the behavior is doing, right? And then I can ask, what type of algorithm is that? What type of thing, you know, now that I've done that, I can answer questions that I couldn't have before if I was just, you know, not doing that, right? So it's productive in one direction. Obviously, it's not the only answer, but, and sorry, I don't want to take away from Jonathan's time, the other Jonathan.
We usually have 3 Jonathans on screen every week somehow,
Okay.
and it's different rotations of Jonathans.
Yeah.
Too many.
Okay.
My main point was the Kantian formulation here is not, I think, a good thing to apply when we're thinking about, say, determinism or calculation, because Kant needs a particular rigidity of laws of nature in order to motivate moral duty from a kind of disinterested standpoint. If we can think of our particular moral responsibilities as laws of nature, then they can't be self-contradictory, and so we can act from them without with disinterested nature. We don't have an interest in acting good. We do so for insofar as it proceeds from a duty. So Kant's not concerned about universal laws of nature, and insofar as he is, he gets them wrong in particular senses, because there are things that we take as universal laws that appear to function in one mode at one level of observation, but contradict one another at other levels of observation. And there's nothing in Kant that'll get you out of that. Kant would have to say that those are not universal laws. So like that was my kind of nitpicky point. But I did have a thing for the other John. So insofar as an algorithm, I would say as a kind of automation of a process of inquiry requires a particularly determinate problem to be applied to, right? So there's some things that we don't have the language to describe the problem we're trying to do. So we can't algorithmatize them, right? And I think what—
You mean deterministic?
Yeah.
In a sense? Oh, well, we have non-deterministic algorithms that you can, I mean, they have different results because they're non-deterministic, but like you can make them, I guess.
Yeah, you can make them, but the problem is, and this I think goes back to the point that I agree with, that if we want to learn something about artificial minds, we need to focus on robots and not minds, because every mind or every intelligent organism that we encounter in experience is embodied in some way and transacts with its environment through its body, and insofar as it transacts with the environment, the ways that it engages in those transactions are expanded or limited by its body. So you can have all the non-deterministic algorithms you want. They won't tell you anything about how we think, right? Until you stick it in a body.
Yeah. So now I'm gonna hedge a bit and then refer to another study on this, which is by Evie Martyr's group, who had worked on the crab ganglion, the somatic gastric ganglion. And so they had showed basically that when you, like, they have this, you know, canonical sort of circuit bit, but it's totally degenerate, right? Like the same computation was solved in a million different ways by the different crab, you know, models. And so they say that, you know, you have this sort of algorithmic description, but the implementation levels can't tell you anything because of the degeneracy of the circuit. So they say you have to look at it at that higher level in order to learn something, right? And so I would say that there's both sides to that. That if you have the robots, you're going to get a different result than if you're just looking at the the algorithm in itself. And one might be more degenerate than the other, and that's even in an artificial system.
But the motivating.
Wait. I'd love to hear our guests' comment on these so far. So.
Yeah. So I did want to say something about the point on Kant, which is that for the people who hadn't read the paper, that he figures as an inspiration for the kind of interpretation that I'm advocating, and it's an inspiration in a particular way. I think this is the core point of his philosophy of science, one of the core points, to the extent that I can make sense of it. But when I was writing that paper, I was actually taking a graduate seminar with Steve Engstrom on the first critique, so that's why that influence spread in. So the core point being that when we talk about science conveying structure in nature, the idea is that we shouldn't just take those structures to be, out there in nature independently of this process of scientific reasoning and cognizing. And so this is basically what I'm saying about the structures that we call computations being implemented in the brain. We just shouldn't say that they're just simply out there in the brain, as opposed to the scientists finding a form in nature through this process of data gathering and building their model. So massaging a form in nature out of these ambiguous signs and massive details that nature provides. So yeah, all of the stuff on ethics and laws of nature is not, as far as I can see, in the picture of how I'm using that point from Kant.
Yeah, and I wasn't necessarily. I didn't think it was, because I struggle to see how you could get that kind of a reading out of Kant. Although I suppose you could if you tried hard enough. But I actually generally agree with your point, and I think I said earlier that one of the values of the perspective is it allows us to look at models as conceptual tools for sense making, right? Producing sense out of the disorganized experience of the thing that we encounter.
Yeah.
I think that's
exactly
realistically the strength of your talk, which is why I haven't really had that much of a question until the Kant thing came up.
Okay, yeah, that's the point.
Okay, Jonathan Flowers, I wonder if you'll stick around for a little bit. We're going to bring on somebody, Kevin, now. And always curious to hear your perspective on whatever happens next.
I know it's getting late for you, Ben. You're being bombarded with all these questions.
No,
just let us know.
That's
when,
fine. I feel wide awake.
Okay.
In fact, it's one of those days that is made possible with this virtual world that I actually gave a talk at 9 a.m. this morning. So it's been a long shift, but I don't feel too tired.
Okay.
We appreciate your time.
Okay, great. All right.
So Kevin is joining us shortly with a question. So, but the basis that we invite people is based on sort of voted questions. Let's see.
Ida, do you want to read his question while he's joining?
Yeah, that's what I was thinking. So he says, granted that computational models don't force us to be literalists, sometimes, often, we do find it reasonable to treat analogical models as somewhat abstracted, idealized literal representations of the target system. When are literalist interpretations of models warranted or not? If they're warranted elsewhere, why do you think they're not warranted in psychology?
Yeah.
There he is.
So hi. I don't know if it's gonna come up. Did you have anything to add to the question before I start?
Kevin? Kevin, we don't see you, but I think we can hear you type. So if you can hear us, you can speak.
I think he was making a black box argument.
We're here for your jokes, John. We're basically mainly here for your jokes.
Well, maybe you can start answering, and then if he's able to speak.
Yeah, sure. So one thing to say is, like, what I mean by a literalist interpretation is quite tied to computationalism and saying that, you know, the brain literally is a computer. But I'm just trying to think, you know, if there are other branches of science where you'd want to say, yeah, there's a literalist take and a non-literalist take. Just trying to think, you know, about a whole like philosophical theory that is built around a literalist take. I mean, what we can say is that, you know, there's models, and there's plenty of models in science which represent the world in ways that are abstract and often idealized. In lots of those cases, it would be, you know, obviously a mistake to be a literalist about them. But yeah, where am I going with this? But at the same time, you know, I'm saying that, sure, no one's going to like believe that all the abstractions and idealizations that are obviously there in models are, you know, we should be taken literally. At the same time, there is this debate amongst philosophers of science about what the significance of those features are in models. So what scientific realists normally say is that what's epistemically valuable about the model is the content which is representationally true, and the abstractions and idealizations are just like heuristic or there for pragmatic reasons. And I tend not to think that. I think more that really the content of the model is not, you can't just separate out the true bits and the false bits and say the true bits are really representing nature and the false bits are not. So that goes along with like my general lack of sympathy with scientific realism. And one of the things that I think makes this literalism problem like more salient in computational neuroscience is just that it's not clear so much that what I'm saying is, you know, a massive abstraction of like ignoring all of these biological theses. It's not clear that that is a massive abstraction or even an idealization or something that's saying something not true about the brain to most people, given our lack of understanding of how the brain really works. Because what I'm saying is the core abstraction here that the computational model framework imports is that there is this clear divide in the brain between what in the brain is really cognizing and what is metabolic support. And so the literalist is taking that abstraction and saying, yeah, it's like there's a division in the brain that is there in nature between the cognizing stuff, which is doing computations, and all of that gunk, which is biological goo and just keeping the neural machinery running. So I'm saying that's a massive an abstraction that people are importing on the brain. The literalist is saying that taking it literally. And I think that's a different case from plenty of other cases of abstraction of models in science, because it's just not obvious on the face of it that that is an abstraction. Some people just think that's how the brain is.
Who's a proponent of this literalist view? Or who are the main proponents of the literalist view?
Yeah, so on a more expanded version of the slides, I had a quote from Gary Marcus saying that, you know, the reason why we should say the brain is a computer is that it takes inputs from the world, does perform some computation on it and gives outputs. I think that's very much there in David Marr as well. I think he's very much a literalist, and I think he's been, of course, extremely influential. And I think it's there in the language of computational neuroscience, just when people, you know, casually describe, you know, their circuit, which they're talking about, and here's the model for it. Oh, this is the computation running in this circuit. Carandini and Hugo stuff on canonical neural computations, I think that's certainly committed to these computations really are the building blocks of cognition, and they're going on there in the brain. So I think there's plenty of examples amongst the scientific community.
Is that, just one quick question about that, is that so different from people who talk about specialized cells and they talk about housekeeping genes, which might be common across all cell types, but then there's a specific differentiated capacity of a particular cell, a fibroblast versus a mesenchymal cell versus is it so wrong to focus on the specialization and just put the housekeeping function into the background?
Yeah, well, the reason why I bring this up is that I think there's at least indications that what is taken for metabolic support or non-cognitive, if you talk about glial cells and I don't know, other stuff that's there in the brain is having some kind of cognitive role. This isn't like my area of expertise because I haven't studied much cellular neuroscience or other stuff like that. But, you know, when I talk to someone that works on neuroendocrinology, and there's so many things that make you think, well, there just isn't that clean division between like information processing and cognizing and just all of the other stuff that's going on in the body. That's what makes me wonder that this is really a division that's being imported for convenience.
Well, that's where functionalism comes in handy, because I think Brad is here. We have Brad. Brad is one of our, one of the people that helps us run the salon, and we're very happy to hear his question.
Or lip read his question.
We're lip reading, Brad. We can't hear you for some reason. Now you're muted. You're unmuted, but we still can't hear you.
We can't see your costume somehow.
Yeah. You're also not in your Star Wars costume. I don't barely recognize you. Oh, barely, you're far. Yeah. If you come closer. We have signal. Better? Perfect. Okay. Awesome.
So first of all, thanks again for the talk. This has been really interesting. I don't have much of a background in philosophy, so I've been struggling to sort of figure out where I place myself in sort of my beliefs about your particular definitions of computationalism and cognitive function. The sort of first thought that I had at the beginning of this, and I'm not sure if it's a particularly great question that can be answered, but can we think of any specific examples of behavior or biological function that would clearly put something outside of the realm of computation as we describe it? I mean, there's been like discussion of, for example, people solving the halting problem as one such example of something like that. I'm not convinced that that's necessarily a great example, because I think that people can use heuristics to solve the halting problem without doing it algorithmically, of course. Have you encountered or come up with any such examples of something like, if we could demonstrate X, then that would sort of be something that we could place it outside of the realm of what we could normally talk about in terms of computation?
Yeah, so it sounds like this is the territory that Roger Penrose was working in. So his book, The Emperor's New Mind, which was a book that he wrote against, arguing against the possibility of strong AI, like human-like AI. So it's based on ideas that, humans have mathematical intuitions that go beyond what is computable. So this is an argument, is that there are cognitive capacities that we have that are not things that a computing machine could share. So it's not the kind of angle that I take, because that's not what my intellectual background is, to think about this kind of stuff. I'm not a mathematician, and yeah, I also because I'm also really interested in the point that about not expecting computers to be able to duplicate the capacities of other animals, not just humans, but that there being stuff that maybe octopuses and monkeys do that you wouldn't be able to build a computer to do, and since those aren't creatures that are doing maths, then that this kind of territory is not so interesting to me. But yeah, it's a line that people have investigated. Yeah,
I mean, it's a hard one, because if you're claiming that these certain kinds of intuitions or decisions are non-computable, then someone can argue, well, maybe they are computable, you just haven't imagined the solution that could be implemented with a computer.
Right.
Yeah, I mean, I take your point, and I think that I haven't really seen a convincing example of something like that beyond like some obvious example of, someone clearly solving a problem in, of a higher order of computing cost in a much lower amount of time than a computer could. But yeah, that was sort of my initial approach in thinking about this, and I completely take your point that that's an orthogonal approach to where you're coming from.
Thanks. Well, thanks for joining in.
Thanks.
Thanks for joining in. Yeah.
So so maybe we can slowly wrap up as we can. We have basically 4 minutes to 6, and it's already very late everywhere else other than the East Coast where we are. There are more questions, of course. There's like 12 more questions, but I think that maybe everyone that's on screen, maybe one last chance to maybe ask a question, or if they have a wrap-up comment.
So I had a thought about Kevin's question with regards to analogy, and the question as to why we don't use the kinds of analogies, e.g. computer for brain, for other biological systems, and what the concern there is. And I think from my broadly Deweyan perspective, it's the overall effect that the brain as computer metaphor has on the broader systems of relation that we're embedded in, right? So saying the brain is a computer and treating this as a kind of motivating impulse in our inquiries is a lot different from saying mitochondria is the powerhouse of the cell, and that has broader social effects for the collective social activity that is science. So insofar as we say rely on a more or less literal interpretation of the analogy, and the same holds true, I think, for computation and calculation and these other computer science terminologies imported here, we need to be cognizant of the broader context in which they're initially used and the broader social effects on science as a social activity, which I is kind of one of the things that comes out of your talk. So I think that's the fundamental difference.
Yeah, I think that's a really important point, that these analogies never occur in a vacuum, and I think that what I really like about Canguilhem's paper, Machine and Organism, which was one of the inspirations for this. This paper was thinking about why people making these comparisons in the context of like economic systems in which certain machines have a labor function which could or could not be performed by an animal or a human, and that these are all relevant to how we're thinking about all of these things in science as well. So it all is very much embedded in a wider society and a history.
So I would just say, as a mostly anti-realist, your view of analogy is, for me, like, yeah, of course, it has to be an analogy. And I'm a big fan of people saying it out loud and making more reasonable arguments than what I just said, which is, I'm an anti-realist, so it's an analogy. Yeah. So I'm grateful. I think, like you said, it's kind of implicit a lot in what goes on in neuroscience, and even if it is true, I think it's still valuable for us to think about the pros and cons of thinking whether it's true. Just as Jonathan was saying, like there are social implications of how science happens, and these analogies or models happen not in a vacuum, as you were saying. So I'm highly in favor of thinking carefully about what it means and who it impacts to say it's a computer, how that changes the dynamics of what we're doing. So thank you.
I think it could
I had a last question. Oh, sorry.
No, go on. Go on, John.
No,
I am yielding the floor to you.
So I guess what I wanted to ask you to finish is, if we want to have some sort of compressible if somebody wants to know how the mind works, and there are ways to sort of provide functionalist, because one thing about functionalism is it allows you to use objects of explanation that aren't far from the phenomenon itself. right? Cummins
yeah.
makes this argument, right, about
Yeah.
cooking, right? Now, I was just wondering whether analogy may just be a explanatory instrument in and of itself. In other words, that maybe what we want, if we're going to ever be able to say, I understand how the mind works in sort of a vaguely functionalist way, that maybe we just need to find the best analogies we can, because analogies work so well in the rest of life, right? I mean, it's amazing how if you want to convey something, you make an analogy and people go, oh, yeah, it's a great analogy, right? So I'm just wondering whether that's what we should be aiming for, rather than it sort of being a criticism. Maybe the best analogy will be the best explanation. What do you have to say about that?
So I'm not calling the computational analogy a computational perspective and analogy or an analogical one in order to criticize it in the way that people say, oh, you know, when people talk about brains as computers, it's just a metaphor and there's nothing to it. I think it gives this explanatory traction, because I think that's what analogies do. And I agree with you. I'm definitely not one of those people that says, you know, we've used too many metaphors for the brain and we just need to describe the brain itself. I think that's mistaken, because it's this idea that you can have some kind of unmediated grasp on things, which isn't making use of concepts that have been developed elsewhere and just taking in everything as it is in itself. So you can just read off a whole new set of concepts out of nowhere. I don't think that's realistic. So yeah, maybe analogies is well, I think yes, analogies are going to be the best that we could do. The warning about the literal interpretation is that it traps you in one set of analogies and maybe stops you exploring other ones, if you don't realize that in an analogy is only an analogy.
That's interesting, right? If it's just an analogy, there could be better ones. Whereas if you think that analogy is literal, you might not find the better analogy.
Right.
Right.
Yeah.
Huh. Okay. Interesting.
I do wonder whether that's basically just saying the brain is functionally equivalent to a computer, but it's not only functionally equivalent to a computer. And so as long as we're not exclusive with regards to the computer and the brain, so the computer being the right metaphor, it seems like we can still be functionalist as long as we're not exclusive that it's just a computer.
Yeah, we can be functionalist in that sense about positing functional equivalences, which is not the ontology of mind, which says that, you know, mental states essentially are computational states. So yeah.
Okay, so now I'm thinking about, for instance, I'm thinking about the papers in the philosophy of mind that I've read with regards to functionalism, and I'm not sure if all of them are as sort of interesting. I have one last question. Are you also an anti-representationalist? Given the embodied cognition and the dynamical systems comments that you made. I know it's a whole other discussion.
Yeah, sure. No, so I'm not as hostile to representations in psychology as most people in that camp. I don't buy into this view that, oh, as soon as you talk about mental representations, you're like trapped in a Cartesian theatre. I think that's a mistaken caricature of what thinking about representations could do. But I think there are problems with literally interpreting talk about neural representation. So that's going to be like another chapter in this project. So I'm more happy thinking about intentionality in psychology than in neural systems. I think it becomes a bit more intangible, and I'm actually quite open to the idea that intentionality is irreducible. So I've been influenced enough by phenomenology to go that way rather than worrying about naturalizing intentionality as well. So that's something else I'm going to explore. But yeah, that's
wow.
Wait, irreducible as in irreducible as in immaterial?
No, just that we shouldn't try and say that ultimately what intentionality is a specific kind of causal process. So naturalizing in terms of like describing what kind of causal steps need to happen, maybe evolutionary or maybe in real time, for something in your head to be a representation. So that's yeah. So
Yeah,
it's
we could start again.
Yeah, we could start again.
How much time did you say? I'm putting coffee.
No.
Yeah, no, but this is a chapter that I'm working on. I haven't got the
book?
details nailed out yet.
What's your book?
So yeah, it's under contract with MIT. It's called How to Simplify the Brain. So it's like a series of case studies of simplification in neuroscience. So there's computational framework being one of them, and then drawing out some philosophical lessons from these. So yeah.
Awesome.
Yeah. I remain a functionalist about mental events, as in, I do think octopus feels pain. And I think Peter Godfrey Smith also claims in his book that octopus has mental states. And, so in spite of his embodied cognition, he has the functionalism in that sense. But I really enjoyed this conversation. And I think you raised very good points. I really, in spite of sort of some philosophical disagreements about whether functionalism is rejected by this perspective or not, I think you made excellent points about perspectives of some of the common people in our field and conferences that we all go to and review for, that the literal interpretation could potentially hold us back in various ways. And not just in philosophy. I think it's so. When I asked you what is the consequence, I don't think it's just a philosophical thing. I do think that maybe not as extreme as the literalist versus anti-functionalist, but the literalist versus something that's a couple of steps away from it. That would be someone like me. That would still be. I think that still leads to different sort of perspective. So I really appreciate you highlighting the spectrum and highlighting the ends of it. It was a fantastic session. Thank you.
Oh, well, thank you very much. No, it's really a pleasure to meet you all and discuss this stuff. No, it's really an honor. So, yeah, and I'll look forward.
Come back.
Yeah, definitely. Right? So I hadn't been able to attend many sessions in person because I'd been moving house a lot most of the semester, starting a new job. But I'm settled now, so I'm planning to be a regular person attending. It's a lot of fun. So
yeah, we look forward to
putting this together.
Thank you so much.
That would be wonderful. Thank you so much. Really.
I would love to see you again.
All right. Take care.
Okay. Thanks.
Thank you, everyone. Thank you.
Have a good weekend. And thanks for your questions. That was really a pleasure.
Thank you.
Bye.